Hi everyone, and welcome to the second video in the series of ENGR 315 lab tutorials. Today we will be looking at first principle modeling. Basically what is going to happen in this lab is that we're going to derive a model for these cube servos in the form of a transfer function. And we're gonna run a simulation on the model that we derived and compare it to an actual experiment that we have with the hardware and see how they compare against each other. The Quanser Cube Servo is a direct drive rotary servo system, meaning that the load, that in this case is the disc that we mount on top of it, is directly connected to the motor, and no other components such as couplings are needed to transfer the motion between the motor and the load. So basically it's not entirely true in this case. We have this again disc looking hub on top of the motor, but that's all that we have that connects the disc to the motor, and there are no other components. So next we'll be deriving the equations that govern the dynamics of the servo mechanism. You can see in this schematic that we have basically an electrical and a mechanical component. On the left we have the electrical components, which represent the motor armature circuit with the current IM that drives the motor, and the back EMF voltage EB, which depends on the angular velocity of the shaft, and the back EMF constant Km. We also have three mechanical components, as you can see. We have the motor, the hub, and the disc, as I mentioned. All these components are rigidly connected to each other and rotate around the same axis. Next, using Kirchhoff's voltage law, we can write this equation, and we can simplify this equation knowing that the motor inductance has a relatively small value. And next we can again rearrange this equation for IM and specify the driving current of the motor as a function of the angular velocity and the voltage. Next we discuss the equations governing the mechanical components of the system and also how they relate to the electrical circuit. So the motor follows this equation. You have the JEQ, which represents the equivalent moment of inertia of all the three components. And also we have the torque of the motor and also the angular acceleration of the motor. In the second equation, we see how the torque of the motor relates to the current that is applied to it. The equivalent moment of inertia in the first equation is basically the summation of the individual inertias of the motor, the hub, and the disc. You can use this table to substitute the parameters in the discussed equations with the numerical values corresponding to Quanser cube servos. Please do not use the JH value, which represents the load hub inertia, and calculated using the half times m times r squared formula that we saw in the previous slide, using the given mass and radius parameters. So this is the Simulink model that we'll be working with this session. As you can see, there are two main components of it. We have the experimental setup on top. We write a signal to it and pick up the readings from the encoder and show the results as a plot in the scope. And we also have the theoretical model that we derived using the equations that were described in the background section of this lab. So in this video, I'm just going to go over the experimental setup, and your TAs will discuss the theoretical simulated model with you in the class. This Simulink block basically represents the experimental setup that we have. All the blocks that we have in this block diagram are the same as the ones that we were using in the first session. We have the same signal generator with the same square wave signal alternating between 1 and 3, and here we're basically again plotting the speed. So if you look at this transfer function here, it's a derivative and a low pass filter combined. So we will have a smooth representation of the angular velocity response of our system when we run this simulation. So just as a recap, I'm just going to go over the initialization steps of the Cube Servo. Before creating this model, I imported the HIL initialize block, selected Cube Servo number 2 as the board type, and also set default options. And after everything in the model has been imported and the blocks are connected to each other, we build the model so that the changes take effect, and in the end run the simulation by pressing start. So in this scope you can see the angular velocity response of the Cube Servo, and also you're able to see the actual response of the disk in the picture-in-picture frame. And with that, we reach the end of this session. Thanks for watching. See you in the next one.